This PAM already we have discussed in the last few classes. So here what is happening is that just I will brief it out. So as far as looking at the previous things what has been asked in the question papers, so no mathematical discussion I have observed there. If it will come into picture later, that also will consider it in future. So what is happening here is that this is your message signal G of t and the train of impulses dou S of t. So here the train of carrier pulses are varied as per the samples of the modulating signal. So how the amplitude here it is varying, the message signal amplitude. Accordingly, these train of impulses got varied. So this is also known as a flat top sampling, as the top of each modulated rectangular pulse is maintained flat here. So the train of pulse you can see here, its a top edge is maintained as flat here. So these things got varied, you can see here, as per the instantaneous amplitude variation of the message signal G of t. So envelope here, you can see that it has been shown by the dotted line, is actually the instantaneous variation of the amplitude of the message signal. That is responsible for the variation of the respective amplitudes of each of these pulses in this P of t, that is a train of pulses. So this is just brief thing I wanted to make it. So next today we'll take into another important discussion, that is a time division multiplexing. We already know it briefly. That is a time division multiplexing means time is the main concept or basis in order to do the multiplexing process. Time division and multiplexing. So two things are there here. We are going to share or divide the time among multiple signals what we want to transmit over the same channel, common channel. You can see here as shown in the figure, message inputs are 1, 2, so on up to capital N. N message signals are there or samples are there that we wanted to transmit it over one communication channel. That is not possible practically, because in that case they are going to be overlapped or will be mixed. So that is only to avoid this mixing or overlapping and to transmit it over single available communication channel, we are using the concept of multiplexing. So in this multiplexing process, n independent signals can be transmitted over single available communication channel without overlapping. So how this could be done? So this can be done in a pattern-wise manner or in another manner, whatever. But we'll see that each signal, each individual signal that we wanted to transmit it over single available channel will get a fraction of time. We'll give some amount of time for a message signal one to you can go through that single communication channel and reach the receiver. And we'll let some another amount of time for the second independent signal and transmit it over single available communication channel and so on up to n. So in this way, we are sharing a different amount of time for each of the individual or independent time domain signals to be transmitted without overlapping or mixing over single available communication channel. And it is called alternating pattern here. Sorry. Okay. And it is called alternating pattern here. So pattern means here is that, so in what fashion the time has been, the fraction of time has been shared between or among these all n independent message signals that we wanted to transmit. So again, it will depend on many factors. Message signal 1 may need less time, or message signal 2 may need more time. Message signal 3 may need more than 1 or less than 2, like that. It may got vary depending on the what amount of information is residing or contained in each of these message signals that we wanted to transmit. So if you consider this one factor, again it is going to have an impact on the pattern at which we are going to distribute or share the time during which the message signals to be transmitted. So, but whatever it is, then some pattern will be there. Suppose if you assume, for example, the time taken by message signals 1 to n will go on increasing. So that is one pattern we can see how we are going to share the time for each of the message input signals to be transmitted from 1 to n in an increasing or decreasing manner, or again increasing, decreasing, some pattern will appear depending on the amount of information and some other parameters. So that is one thing. So again, each of the individual message signals will be first passed through the low pass filters, which are known as pre-alias filters here. So these low pass filter will see that each of the message signals, of course, we are already telling them as independent, will ensure that they are band limited and will not got overlapped with each other. So that's the job of these low pass filters, which are also taking care of the aliasing effect. So each of the n signals should not be got overlapped. Along with the low pass filter means high frequency components will be avoided, which will normally contain the noise. Any additive or hidden noise will not be allowed to pass it through and got multiplexed. Okay. So here low pass filter has got two important jobs here. One, it will not avoid it has to avoid the high frequency noise signals. And second thing, pre-aliasing. These are also known as pre-aliasing. So why they are called as pre-aliasing? Because aliasing effect should be avoided between each of these independent n signals. And it is called pre-alias because we are ensuring that each of these low pass filtered message signals should not be got overlapped. Aliasing effect will be avoided in the preliminary stage, pre-stage. That's why this is known as pre-alias filters. Before multiplexing, we are ensuring this aliasing effect should not occur. So that is another important responsibility of the low pass filters. So that's why these are also known as pre-alias filters. So after doing this one important step, pre-aliasing filtering step, so each of the n independent message signals now got undergoing multiplexing process with the help of the commutation or commutator. Commutator is a device which will have two important steps to do. The first thing, it will take a narrow sample of each of these n samples. It's something like, for example, the message input signal after passing through low pass filter, I am telling. Okay. So when message now at the output of low pass filter, your message signal one will appear like a stream or train of pulses. In some format, it will be there. Some frame will be there, frame of bits. Okay. So this message input signal, now we can view it as a train of bits or a group of bits. That is known as a word. Or if I will call a group of words, means it is a group of, it is a set of group of bits. That is what we mean by words. So we can view each of these messages as a group of bits or words. So this commutator, what it is doing, either it simply do one thing. It will take some bits from one sample of bits, some sample of bits from two, some sample of bits from three, and so on up to n. And it will interleave. It will interleave all these bits. sample of bits, whatever it has taken from 1, 2, and so on up to n. Or else, that is one thing with respect to bit interleaving. Means commutator can interleave the bits in the form of a bit interleaving, or it can take the sample of words from 1 or sample of words from 2 and so on to n. It will do interleaving of words in the form of word interleaving. Means we can adopt as per the requirement either bit or word interleaving in this way, taking n samples or words at a time at the rate what? Greater than or equal to the w. This is the important condition. That is aliasing condition. So when you are interleaving them, so we will see that they will not overlap with the particular guard band should be there. So that will ensure that they will not be mixed or overlapped within each other. Second thing, sequentially will interleave one after the two, and two after the two, three after the three and four. Or else, if you want, you can follow the pattern. Can go for with all odd or all even, something like that. But some pattern should be there when you are going to do the interleaving. That's why it is known as a sequential interleaving. So that is exactly what I mean by multiplexing. Multiplexing exact words, if you want to tell, it is a sequential interleaving of the n samples. With the sample interval, means they should be spaced with this much of interval, 1 by fs. So they should be taken at the rate of n samples from each of these n channels, you can say. Each individual signal now acting like a channel. So they should be taken at fs samples, n samples, and they will be spaced when you are going to interleave them. They should be spaced at 1 by fs at a time. These two conditions that will ensure sampling theorem should be followed and aliasing effect will be avoided. So this is the main job of the commutator. So here we'll be having one commutator. This is up to this one. At the this is known as a transmitter up to this one. So what we did in transmitter, we'll do the low pass filtering and commutation. Same thing will be there at the receiver side. Decommutator and low pass filters will be there. Again, they will be got synchronized properly. They will be got synchronized. Okay. So over the communication channel, what we are getting between the transmitter and receiver, you can see here. So one thing we got understood that at both transmitter and receiver, we got the symmetrical or synchronized circuits will be there, which are operating in hand together. Low pass filters or commutators. So in between, you got the channel. So in between, after the commutator, what we'll have? We'll have the pulse amplitude modulation. Timing pulses will be there. So pulse amplitude modulation will be done and transmitted over single communication channel. Pulse amplitude detection will be there. So after this pulse amplitude modulation, we have the transmitter, and demodulation will have the receiver will start from that stage. So in this way, so after doing the pulse amplitude modulation, that's already we have discussed there. Your multiplexed, time division multiplexed, and pulse amplitude modulated signal is transmitted through the single available communication channel. Then at the receiver, pulse amplitude detection will be happening. Each of the pulses will be detected, and decommutator here you can say it will start redistributing the pulses of the respective channels 1, 2 and so on up to n message signals. Again here, reconstruction of each of these message signals from the received samples will be start happening independently, and we will start getting receiving the independent message signals from 1 to n. So in this way, guys, sometimes you'll get a short note on this one. You have to draw this neat block diagram. And main thing is that you have to explain the main things what is happening here in the pre-alias filters, commutators, PAMs, and how the transmitter and receivers are going to work in hand in together or synchronized manner to explain this time division multiplexing concept. So next one, another important concept today we have to discuss is a pulse position modulation, or also known as pulse duration modulation. So here, if you look at this accurate statement here, samples of the message signal, here you can see m of t has been shown here, a continuous time modulating signal m of t is used to vary the duration of the individual pulses. So either you can, if you vary the duration of the pulses, then it is known as a pulse duration wave. And if you vary the position of the pulses of the carriers, then it is known as a pulse position modulation. That's all. There are two versions, pulse position or pulse duration modulation. Let us see here. This diagram will help you to understand this simple concept. Here we got the modulating signal, low frequency, low amplitude modulating signal, m of t is there. And if you look at this one, its amplitude is instantaneously varying. And second figure, we got the a train of pulses of the carrier signal. So these pulses we have to vary according to the amplitude variation of the modulating signal. How you vary? Either you vary, so before modulation you can see all the pulses of the carrier have got the same width and same height. So we have to vary either its width, that is known as the duration, that is according to the amplitude variation of the modulating signal, or else you can vary the position, sorry, or else either you can vary the position of the pulses of the carrier with respect to the variation of the instantaneous variation of the magnitude of the modulating signal. Then we will get the pulse position wave. So this is the normal equation, standard equation we are following as shown in equation number 1. If you consider TS as a sample duration, using the samples, that is m of nts, m of t is a measure signal. With the ts duration, we will get it as m of nts samples of this measure signal m of t. To modulate the position of the nth pulse, we get the ppm signal as a g of t of n minus g of t minus nts minus kp of m of nts, where kp is the sensitivity of the ppm. So this one equation you have to describe here when you want to define and explain about this ppm or PDM. So, that's all about the TDM and ppm or PDM. So let us try to understand how we can generate these ppm signals. Pulse position. Okay, we are going to vary the position of the pulses in the carrier signal according to the amplitude variation of the modulating signal. Here we got the sample and hold circuit first. The message signal is applied as input. So this message signal, this is continuously varying, no. So this one is now applied as input to the sample and hold circuit. What sample and hold circuit would do? It will cut your continuous time signal m of t into samples like this, and it will hold for the time being. You can see here, u of t is the output of sample and hold circuit. So each of the sample, what we got, it will be held in its respective position for the time being. That is u of t here. That is output of sample and hold circuit. From continuous time signal, you are getting this kind of a version of sample and hold circuit, hold waveform we are getting. Now here you can see at the sample and circuit, it is getting the pulses as input to generate these samples and held for the time being according to the instantaneous amplitude variation of the m of t. And same pulses will be given as input to the sawtooth waveform generator. So sawtooth waveform is like this. So later what will happen after getting such kind of sample and hold waveform? This will be added with this sawtooth waveform, which will be generated from the sawtooth generator. So both this kind of U of t and the sawtooth waveform generator C, we are getting with the help of this pulse generation. Pulse generator is required for both the blocks here, sample and hold and sawtooth generator. Now we can see U of t, now we are going to add with this sawtooth waveform. So after adding these two, we are getting a V of t signal as it has been shown here. Little bit amplified and little bit got varying according to the envelope of that your message signal. This one, envelope of the message signal. Only sample of that I have shown here. Now this V of t now applied to as input to the threshold regulator. So what this threshold regulator will do, as the name suggests here. So whenever this V of t will cross the 0, okay, this will be detected. 0 crossing will be detected. It is going to generate one pulse. So listen here. Threshold detector, what it will be doing? It is detecting whenever this V of t is crossing the 0 and generating one pulse. Such kind of pulse you can see here. That is known as I of t. So later this will be fed as input to pulse shaping filter to properly shape it, so that we will get PPM signal here, S of t. So in this way, guys, later I am updating that one, upload that one. You can refer to the notes. So, or you can refer to the textbook also. So very brief explanation is given. Like that, you need to explain how we are going to generate the PPM waves. Next, how to detect the PPM, such kind of PPM signals. So these are the PPM signals now you got. Okay, how to detect them? First, we'll convert the received PPM wave into a PDM wave, duration wave, with the same modulation concept. You can see here, PPM is now converted to PDM wave, and PDM means 1 minute. So this one is your PPM wave. This will be converted to PAM, sorry, PDM wave, pulse duration wave. Means the duration of each pulse got varied. And obviously each pulse, as its width has got varied, will be having a different area under curve. So that we need to find out. So that can be done next step by integrating it. So after first converting such PPM wave into PDM wave, our next job is resides with calculating the area under each of the different pulse of the PDM by using integration. So that's why that is the second step. Integrating this PDM wave with the finite integration time. So idea here is we are computing the area under each of the pulse of PDM wave. Then next we'll sample out the output of integrator at the uniform rate to get the PAM with the pulse amplitudes proportional to the M of NTS of the original PPM signal. So finally we'll apply this one after sampling and integrating this one to the demodulator to demodulate the PM wave to recover our message signal M. So this has been briefly summarized here in the figure here. So normally you will get one, many times I observed here. So based on this PPM, you have to explain its concept with this figure and the standard equation. And you have to show with this block diagram with the neat waveforms here how the generation of PPM could be done and how this generated PPM can be used to detect the PPM with brief out of this waveforms here. So next one, another concept what we are getting is a noise in PPM. Because in pulse position modulation, our information is contained in the form of each of the pulses. Okay, information is there in the each of the pulse. And if some noise will be added in each of the pulses, then it is going to affect the performance. Assuming the full sinusoidal modulation, full load means full sinusoidal modulation. Output signal to noise ratio is given by this, SN or not. Pi square BT, that is a bandwidth, band limited signals. TS, the sampling duration of each of the pulse, A square by 32 N naught. So the channel signal to noise ratio, next SNRC is given with the average noise power in the message signal given by this formula. So I'm putting the formulas here directly later because it will be suitable for me to find out figure of merit. That is the ratio of SNR naught by SNRC. We are not guys going deep in about these derivations unless if it is confirmed later. If it has been asked, if you one of you can tell me, we'll go about that one later. You can also refer to the question papers. As far as I have seen, this syllabus has been revised here. We'll see it. If it has been asked, can go later. If we substitute here, divide the SNR dot by SNRC, finally we are getting this another important formula for our PPM system. So further things are based on the, up to this sampling is over. So further things, sampling is there, that we'll see in the next session.